Hello, everybody. Welcome to today's lecture for MME 2305 Material and Energy Balances. We've moved on from the material balances and we're now in the energy balances. So we're talking about energy balances part one. I'm your professor, David Robertson. What we're going to talk about for pretty much until the end of the semester is energy balances, and that entails the first law of thermodynamics. Energy, heat, work, and enthalpy are pretty much the main things we're going to cover. Excuse me. Energy is hard to define in a lot of ways, actually. It comes in many forms. And so kinetic energy, we have this equation, the classical Newtonian kinetic energy equation. So kinetic energy equals 1/2 mv squared. The change in kinetic energy ends up being of interest to this class, and so we can have a change in kinetic energy by expressing it in terms of change in velocity, and that's a change in kinetic energy. The energy associated with a translational motion of a system relative to some frame of reference, the surface of the Earth, is one way to define it. Potential energy, you always think about you raise something to a higher level, you increase potential energy. So that energy is associated with the position of a system in an electrical, gravitational, or magnetic field. And so the change in potential energy is of interest to this class. And we usually change our potential energy by changing the height. Internal energy is any energy other than kinetic or potential energy. So don't ever forget that. And it's denoted as U. And one thing to remember, just like matter, you can neither create nor destroy energy. So energy can neither be created nor destroyed, but it can be converted into some other form. And we see that a lot of times in life. These three energy forms are non-transitory, and we'll get into talking about what non-transitory is as the lecture. In terms of flow rates, we simply just put a dot over things, and we've seen that in the past. So we have energy rate, or rate of change in kinetic energy, is given by 1/2 times the mass flow rate times the velocity squared. And the change of potential energy is the mass flow rate times gravity times z. We can split this out a little bit, where we express our change of potential energy in terms of changing our z height, and we can do the same for our kinetic energy as we saw before, where we can change the velocity in terms of rates. Energy crosses a system in our system boundaries in two ways, and heat and work are the ways that energy crosses system boundaries, and the direction of the way it was transferred is denoted by sign. So if we add heat to the system, our value is positive. If the system's giving off heat, it's negative. If we, excuse me, if the system does work, it's positive, and if work's done to the system, it's negative. And so work can be I like this definition: energy that flows for a reason other than a temperature difference, electrical or mechanical. And heat is a transfer of energy due to a temperature difference, and that's denoted as Q. Heat and work are transitory, and they're transitory because they cross the system. Kinetic and potential energy don't really cross the system. We have types of systems, and so we have open, so mass and energy cross system boundaries, and most of the problems we have done, like our distillation problems and stuff like that, are open systems. Closed systems, mass and energy not cross system boundaries. That's like baking cookies. It's also many batch processes are closed. And then isolated systems are not very common. A thermos is a good example. Your Yeti cooler is another. Baking cookies is closed, but it's not necessarily isolated, and we've talked about that before, how you can kind of see steam coming off of an oven. Units of energy, we usually use the joule. Joule is also Newton meter, so joules is newtons times meters, or the foot-pound force. And the amount of energy is different for a given process. And so we kind of have these examples. So nuclear fission of uranium is 1.6 times 10 to the negative, times 10 to the 6 kilojoules, negative 1.6 times 10 to the 10 kilojoules. Ionization of the hydrogen atom is 2 times 10 to the 3 kilojoules. Oxidation of hydrogen water molecule to water vapor is negative 2.4 kilojoules and so forth. And you can kind of see different processes have different energies. Here's a change of potential energy. So lifting a nickel from the floor to 300 meters in the air is 160 joules in potential energy. So the signs denote relationship with the system. So signs are kind of important, and we'll be working some problems shortly where we kind of look at the signs sometimes. So pay attention to that. Energy is heat, and kilocalorie is 1, and gram calorie or British thermal unit or other forms of or other units of heat. Joule is of course the other one. Joule's law, you can get heat out of an electrical circuit through Joule's law, so Q equals R squared RT. It's also called ohmic heating from Ohm's law. You have two variables, current and resistance, from Ohm's law in joules, in the joules. Let's take a look at an example. And so this is an example of kinetic energy, and it's a water flowing through a 2 centimeter ID pipe at a rate of 2 cubic meters per hour. And so that's a volumetric flow rate, and we want to calculate the kinetic energy for this stream in joules per second using this equation. So rate of kinetic energy equals 1/2 mass flow rate times velocity squared. So let's work this one out, shall we? All right, so we're looking at example 7.2-1 from the book. This is a printout of the previous slide. And we have water flowing through a 2 centimeter inner diameter pipe at a rate of 2 cubic meters per hour. And we want to calculate the kinetic energy for the stream in terms of joules per second. So if you notice, we have our classic Newtonian equation, U equals 1/2 mv squared, but we have it in terms of rates, where we have our energy with the dot, so it's energy rate equals 1/2 mass flow rate, so that's how we're getting an energy rate times velocity squared. And we have some kind of two tidbits in this problem. So we say 2 centimeter ID. So we have this pipe, and all ID stands for, if you're not familiar with it, is inner diameter. And so that's 2 centimeters. So I'm kind of repeating myself a little bit, but inner diameter equals 2 centimeters. We want to know our inner diameter because we need area. Why do we need area? Because we need to find the velocity. So we want to first find the velocity. And to find the velocity, velocity equals the volumetric flow rate over the area. Area equals, it's my attempt to write pi r squared. Kind of went over to the edge. Sorry about that, but we know area equals pi r squared, and so that's our given diameter. So we want to calculate our velocity. I'm writing it out simply because there's two V's in this problem. So our volumetric flow rate is 2.00 cubic meters per hour. We want to convert to centimeters somewhere, just so we can kind of match our units. So we have 100 centimeters squared is equal to 1 meter squared. And why did I choose to use centimeters squared? Simply because we're going to deal with area, because we're dividing our volumetric flow rate by our area, and our area is going to be in terms of centimeters squared based on this diameter. So pi times 1 centimeter squared is our area. Then we were asked to solve for things in terms of joules per second. Usually I don't have people convert time unless it's asked for. In this case, it was asked for, so joules per second. So 1 hour, so our time is going to cancel, is 3,600 seconds. So our velocity is equal to 1.77 meters per second, because our units cancel. I didn't go through that, but our units cancel out. We're going to now find our mass flow rate. All right, so second, we want to find the mass. To find the mass, we can start by our volumetric flow rate. And if you remember, if you want to go from mass to volumetric flow rate and vice versa, we need density. And it's water. And so we know the density of water, hopefully like we know the back of our hands by now. So we can start with, again, our volumetric flow rate. Which is 2.00 cubic meters per hour. Our density of water is 1,000 kilograms per cubic meter. Which is one of the constants, I guess. And again, 1 hour is 3,600 seconds. And so that equals 0.556 kilograms per second. All right, so we have two things we need, because if you remember, E K equals 1/2 mv squared. So we have everything we need to know to calculate our kinetic energy. And there's going to be a conversion that we're going to have to use. So we have a conversion factor that we need to kind of consider, and it'll become more apparent when I actually do the calculation, but we want to remember that 1 Newton is 1 kilogram meter per second squared, because energy in this part of the class is pretty much always in joules, and we'll see some more examples of that. So we just want to set up our energy kinetic, and that equals to 1/2. We have our mass flow rate is 0.556 kilograms per second. We have our other calculation that we got, which was the velocity, and that's going to be squared. So 1.77 meters squared per second squared. And we want to have our 1 Newton is 1 Newton is 1 kilogram times meters per second squared. So I work it out. Energy kinetic is 0.870. We work out the units. We get newtons times meters over seconds. And I just said that we're dealing with energy, and energy in this case is a joule. And the other word for joule is a Newton meter, or equivalent for joule is Newton meter. So 1 joule equals a Newton meter. So this is 0.870 joules per second, which is perfect. We have energy in terms of a rate, and so that's how we work out that example. All right, so let's take a quick look at an example of a change in potential energy. It's 7.2-2 in the book, and we have a crude oil pumped at a rate of 15 kilograms per second. That's a mass flow rate from a point 220 meters below the Earth's surface to a point 20 meters above the ground level. What is the rate of change in that potential energy? We want to remember that the rate of change in potential energy is equal to the mass flow rate times the acceleration due to gravity times height. And we can rewrite it in terms of something changing, P2 minus P1, or potential energy 2 minus potential energy 1 equals mass flow rate times gravity times your change in height. And just kind of think that way. I always think for this problem in particular, it helps picture. And so I have painstakingly put together a picture kind of showing what we're talking about. And so let's work it out. Alrighty, so now we're looking at 7.2-2. And this is an example of the change in potential energy. And we were talking about crude oil being pumped at a rate of 15 kilograms per second from a point 220 meters below the Earth's surface to a point 20 meters above the ground level. And we want to know what the rate of change in potential energy is for this situation. And in the slide, I have a nicer picture, but it helps to draw a picture. And if you take the Earth's surface is a 0 point reference point, we see that 220 meters below the Earth's surface is negative, and 20 meters above the Earth's surface is positive. And that becomes important. The sign becomes important in this calculation, and we'll see why as we work it out. So we want to remember that it kind of helps write things out. So we have our mass flow rate here, and the mass flow rate is 15 kilograms per second. Yay. One thing we don't want to forget is our change of potential energy, our delta E dot P equals the potential energy at a point 2 minus the potential energy at point 1, and that is equal to our mass flow rate times gravity, which is a constant, so we're dealing with the gravity of Earth. And here's where the sign comes in, Z2, so this is Z height minus Z1. And so we want to kind of take that equation into consideration, because the change in Z is what's going to dictate our change in rate of potential energy, or rate of change in potential energy, excuse me. And that's ends up being dictated by the change in Z height. And based on our little picture here, we see that we need to consider some signs when we do Z2 and Z1. Anyways, let's just work it out. So our delta E sub P equals our mass flow rate rather, so we don't have to go from a volumetric flow rate to a mass flow rate like we did in the other example, is 15 kilograms per second. We have gravity, and I remember learning this a long time ago, that the gravity of our Earth's gravity is, or the acceleration due to Earth's gravity rather, is 9.81 meters per second squared. Meters per second squared. And that's an M. If you guys don't read my poor writing. We use our same conversion factors, so 1 Newton is a kilogram times meter per second squared. So we're going to have some nice unit cancellations, excuse me. And we're going to have our change in Z. And again, this is one of those cases where the problem kind of works itself out, because we know we want to get Newton meters per second. We're missing newtons, and so what will give us, we're missing meters, and what's going to give us that meters is this delta Z height. And so our Z2 is 20, and that's minus, and here's where the sign comes in, negative 220 meters. And sorry, I'm kind of going off the edge of my engineering paper. Going to bracket that in, and if I work it out, I punch the numbers in my calculator. The change in energy is roughly 35,300 Newton meters per second, or Newton times meters is joules, so 35,300 joules per second. And so that's the end of that example. All right, so we talk a little bit about the derivation of the first law of thermodynamics, and we have to consider things in terms of a system. And so we have stuff coming in and stuff coming out of the system, and we've done that in our mass balance portion of the class. And so the movement of mass gives us both kinetic energy and potential energy. And so we have kinetic and potential energy coming in and kinetic and potential energy coming out. We also have heat coming in. This crude derivation of the first law of thermodynamics, and I apologize for kind of the poor quality of this image, but we'll go through it really quick. I have a much nicer slide coming up. So the change in energy from the whole system is made up of these little components. Okay, so we have a mass. That mass coming in has internal energy, kinetic energy, and potential energy. The mass coming out also has internal energy, kinetic energy, and potential energy. And then you have the whole system, which has a change in heat associated with it, and also a change of work associated with it, whether work is being done to the system or being done by the system. We can rewrite this equation in terms of a summation. And so this is all of the components. So maybe we have 5 process streams coming in or something. And so it's all of the internal energy, kinetic energy, potential energy for all the components of both the input and the output stream. The work done to or by the system is still one component, and so is the heat as well. If we say there's no kinetic energy and no potential energy, we basically start saying the change in energy for the total system is related to the internal energy and the heat and also the work. If it's a closed system, which a lot of our systems are closed, we have no mass crossing the boundary. The change in energy is simply equal to the change in heat minus the change in work. And so we can rewrite this. The change in energy in a closed system is equal to the change in internal energy of that closed system, which is equal to the change in heat minus the change in work for that closed system. We want to make some kind of general statements about the first law of thermodynamics, and this looks very, very familiar to our mass balance problem, where we say input equals output plus accumulation. In general, input equals output in a lot of the problems we've worked out. This is called the energy balance equation because we're not talking about mass, we're talking about energy this time. If you look at page 318 in the book, the final system energy minus the initial system energy equals the net energy transfer in or out of the system, which is always in the form of heat and work. So our final system energy, and in this case, we're taking into account kinetic energy, potential energy, and internal energy, minus the initial system energy, internal energy, kinetic energy, and potential energy, and heat minus work. And I kind of verbally said that. We can rewrite it in terms of delta, or change in energy. So change in energy equals change in internal energy plus the change in kinetic energy plus the change in kinetic potential energy equals Q minus W. We can get to this where we say there's no kinetic or potential energy because no mass is crossing the system boundaries. If we assume that delta E equals delta U equals Q minus W, this is kind of an important thing. This is also called conservation of energy, or the first law of thermodynamics. All right, so we're talking about types of work that we see in the world, and we have PV work, magnetic field work, shaft work, and flow work. I will tell you that most of the work done in this class is PV work. From the Felder and Rousseau book, we have total work is shaft work plus flow work. We don't do much in terms of shaft work in metallurgical processes. We do some flow work because we do shove things through process units, and we've seen input equals output, that kind of thing in our early. We're going to go through an example of flow work, and it's an incompressible fluid flowing into a chamber with a pressure of 5 newtons per meter squared at a flow rate of 2 cubic meters per second. In the chamber, the pressure is increased by 5 newtons per meter squared, and the fluid exits the chamber with a flow rate of 4 cubic meters per second. What is the flow work rate done on this fluid? And so we want to remember that work is pressure times volumetric flow rate, so it's PV work. In terms of flow work, it's work out minus work in. All right, so we're taking a look here at example 3, and it's basically flow work, and we want to kind of take a look at things in terms of units. So work, the units of work are Newton meters per second, and we've seen that Newton meters per second also equals Joule second in our previous examples that we worked out today. We say that work equals PV, so pressure times volumetric flow rate. And if we remember, the units of pressure are Newton per meter squared, and the units of volumetric flow rate are, in this case, cubic meters per second. We see that the units are going to cancel out, so we're going to get Newton meters per second. So kind of unit analysis, I guess we could say that's what we're doing here to kind of prove that work does indeed equal pressure times volumetric flow rate. So it's PV work. That's what it is. We've also kind of talked about work flow. So the work, or the rate of flow work equals P out V out minus P in V in. And we know from the problem that P out is 10 newtons per meter squared. P in is 5 Newton per meter squared. And we know it's 10 because it said it was increased by 5 in the chamber. We know that our V out is 4 cubic meters per second, and our V in is 2 cubic meters per second. So if we want to calculate our workflow, our workflow rate based on this water going into a chamber or fluid flowing into a chamber, we just simply plug everything in and work out this problem. So workflow equals 10 Newton per meter squared, whistling, 4 meters cubed per second, minus 5 newtons per meter squared times 2 meters cubed per second. And again, our units are going to cancel, so we're going to get newton meters per second, so joules per second, which is exactly the units we want. By my math, we have 40 Newton meters per second minus 20. Sorry, excuse me. 10. 2 times 5 is 10. Newton meters per second. And so 40 minus 10 is 30. 30 Newton meters per second, or 30 joules per second. So that's an example of calculating flow work, and hopefully it is not too daunting. We're talking about internal energy now. So we've talked about potential energy and kinetic energy. Now we're going to talk about internal energy. We said that most of the problems that we're going to talk about in this class are PV type of problems, or pressure volume types of problems. And so if we think about PV, the simplest example is that of a balloon. So the balloon pressure volume work is done as the balloon expands against its surroundings. And so always kind of envision the balloon. There's types of processes that involve PV work. There's isochoric, isobaric, adiabatic, and isothermal. So let's take a closer look at these 4 processes. Alrighty, so we're talking about these 4 different types of processes: isochoric, isobaric, adiabatic, and isothermal. And we have to remember that we're in a situation where there's no change in kinetic energy and no change in potential energy. So E sub K, E sub P equal to 0. So what we're left with is delta U, and if we're dealing with a process for delta U, it is the internal energy final minus the internal energy initial, and that equals Q minus W. We can rewrite this to say that delta U equals Q minus W, or heat minus work. The first process we named was isochoric. And it's also called isovolumetric. That's because it's a constant volume. And that means no work. So here, delta U, since there's no work, delta U simply equals Q, but we wanted to denote Q with a V because it means constant volume. Isochoric. The next process we talked about was isobaric. And if you're thinking, man, bar is a measure of pressure, and iso means 1, so 1 pressure or constant pressure. I was giving some advice to somebody earlier about espresso machines, and I said, be sure and buy one with a 12 bar pump, because that's the pressure. A lot of cyclists use bar as to measure the pressure on their tires instead of PSI. So it's constant pressure. And work is P delta V. So pressure, which is constant, times a change in volume, so something's changing. We can take our delta U equals Q minus W equation here and rewrite it. Delta U equals Q minus P delta V. We can kind of rearrange this equation and write delta U plus P delta V equals Q, and again we're doing P because it's constant pressure. Change in pressure, heat at a constant pressure, is related to enthalpy, and it's equal to enthalpy. We'll talk more about enthalpy in our next lecture. But delta H equals enthalpy, and that equals Q at a constant pressure. So we can rewrite this equation, delta U plus P delta V equals delta H. So that's an isobaric process. The next process that we listed or we talked about was adiabatic. And in adiabatic, I always remember Dr. Stafford talking about adiabatic shear bands, and it always forever sticks into my mind. So adiabatic means no heat. So Q equals to 0. We're talking about a process, so the thing we care about is, excuse me, the thing we care about is a process. So work equals the integral from the initial to the final state of your process times pressure dV. And so then we can rewrite this in terms of delta U. So delta U equals negative P delta V, but R, and R is reversible. So it's a reversible process. This is the delta. And I didn't go through the integral, but it should be pretty straightforward. The next process we talked about was isothermal. And isothermal, delta U is 0. It's a constant temperature. So delta U equals to 0. So Q then is equal to W. And again, we're dealing with a process, and we have this equation again. But this time we're solving for the ideal gas law. And so we have PV equals nRT. So this is for an ideal gas. And so we can rewrite this equation in terms of the ideal gas law. We can pull out the N. So we've put our volume on the bottom, so we're substituting, we're saying what P is equal to, so we can say P equals nRT over V, and I screwed up a little bit, so V equals nRT over P, and then we're solving, we're plugging it in, basically. Actually, no, I was right the first time. Sorry. So we have to remember this rule, that the integral initial to final of 1 over x dx equals to the ln, or the natural log of xf over xi. So we can rewrite this equation, work equals nRT or nRT pi over pf. And sorry about my mistake there. All right, so let's take a quick look at an energy balance on a closed system. This is example 7.3 in the book, and it's kind of a two-step process involving a piston. And so we have this piston, and it had 2 kilocalories transferred to it, but a clamp's holding the piston in place. The temperature is reaching 100 degrees Celsius, and it started off at 25 degrees Celsius. So what is the change in internal energy? You've heated up, and they're using units that we don't use all the time in this class, like calories. I tend to use joules. But anyway, you're heating it up. You've put this clamp in place so it can't expand. So it's a constant volume process. So you're putting in a bunch of heat, basically. And so you've reached this final state of 100 degrees C. The second step is you've released the clamp, and now it does 100 joules of work. And so we're saying, what's the change in internal energy? So it's 2 steps. So we have this first step where we have this piston, we clamp it. We start off at 25 degrees C, and we heat it up to 100 degrees C. It helps to remember our general equation. So delta E, or change in energy, equals change in internal energy, plus change in kinetic energy, plus change in potential energy, and that happens to equal heat minus work. We can simplify it a little bit and think of things: delta U equals delta E K plus delta E sub P equals Q minus W. There's no mass really involved in this process. So these guys are equal to 0. There's also no work. So this is isochoric problem. So we said it's constant volume. So delta U equals Q. So Q is simply equal to the heat that we've put in. I went ahead and converted it to joules because we deal with joules in this class. And so we cancel out. We use our conversion 0.23901 calories per joule. And we get 83.7 kilojoules, or 83,678 joules. The second step, we have this initial step, we have this final state, and we're trying to figure out change in internal energy. Well, again, we start off with our equation delta U plus delta E sub K plus delta E sub P equals Q minus W. These are all equal to 0. So why is delta U equal to 0? Internal energy change is equal to 0 in this case because there's no change in temperature. It's a constant temperature. So constant temperature leads to no change in internal energy. That's also isothermal. So an isothermal process, 0 equals Q minus W, or really Q equals W if it's an isothermal process. So that equals 100 joules. So let's take a look at another isothermal example. Just joking. We have oxygen in O2 form placed in a closed system. The gas is compressed. The initial conditions are 100 liters of O2 at 1.5 atm and a temperature of 400 Kelvin. The gas is compressed reversibly and isothermally until the pressure reaches 6.5 atmospheres. How much work was done to compress the gas? And let's work this one out, shall we? All right, so we have our other example of an isothermal problem. And so we have O2 in a chamber. And our initial state is, what did we say it was? 100 liters at 1.5 ATM. And a temperature of 400 K. And it's isothermal, so it's going to stay that way. And so we compress it, and we have two pressures that we got to deal with. And so our second pressure is 6.5 ATM. And so we just said earlier that Q equals W equals to nRT ln VF over VI, but we're given two pressures, 1.5 ATM and 6.5 ATM. And so just so happens that it also equals to nRT ln PI over PF. And so what's left for us to do is calculate the number of moles and we also have to deal with our gas constant, R. And there's multiple flavors of the gas constant, and we'll use two the solvency of this problem. So first find moles. And there's other ways to do this, but let's go ahead and do the ideal gas law. So PV equals nRT, N equals PV over RT. And so we can find it based on our initial conditions. And so our initial conditions were 1.5 ATM. Over 0.0826, so this is the gas constant we're going to use, is 0.0 liters times ATM over gram moles Kelvin, because it seems to kind of make sense. And so 0.826, 0.0826. And our gram moles is going to end up on top, so that's what we want. Volume was 100 liters, and our temperature was 400 K. Yay. And so things are going to cancel out. ATM cancels out, liters cancels out, Kelvin cancels out. We're left with gram moles. So number of moles turns out to be equal to about 4.57 moles. And so now we're just left with a nice plug and chug. So we can say Q equals W equals nRT ln PI over PF. So pressure initial over pressure final. We want joules. And Just so happens that there's a gas constant that gives us our units, joules. If you kind of just look at this equation, your units of pressure are going to cancel. Our gas constant is going to involve joules per mole Kelvin, and it's 8.314 joules per mole Kelvin or Kelvin mole, depending on your point of view, I guess. And so our units are gonna work out quite nicely. Q equals W equals, just figured this out, so 4.57 times 8.314 joules per mole Kelvin times our temperature of 400 Kelvin. And then this is ln, so pi is 1.5 atm, and our pf is 6.5 atm. And then I plug and chug through my calculator. So Q equals W equals negative 2200 290 joules. And the sign is negative. And so think about what that means in terms of things crossing system boundaries, because that becomes kind of interesting and important.